start by thanking the local organizers, and in particular Martin Boddemann, and in particular Katrin Wendland, for organizing this very successful conference. Now, I've organized many conferences myself, but and so I know what effort it is. But when you then add to it the uncertainty of COVID and also an online component, it really is a lot of effort. So please join me in thanking your local organizers of this conference. So, and I also want to thank Martin, who's really the backbone of this geometric quantization conference. He has persevered through time, made sure it was organized from the scientific committee standpoint, and pushed on, helped with financial support over and over again. So could you please join me in thanking Martin for his efforts all through time. So thank you, Martin. And then maybe I can start with my lecture. So I will start at a point where I'm sure that all of you is very familiar. So namely the general direct quantization actions. So, in quantum mechanics, the classical phase space is really a symplectic manifold. And the general paradigm for quantization is that we replace this with a Hilbert space. The unit vectors then becomes the states in the space as opposed to the classical points in the manifold. Further, we also quantize observables, of course. Now, for observables, classically are functions on the phase space. And so we imagine that they go under some kind of process to operators acting on this Hilbert space. Now, these operators here, they are typically unbounded operators acting on a dense subspace of the Hilbert space, and we require that they're formally self-adjoint if we're talking about real observables. And so we have these three well-known actions of Dirac. The operation hat here, which is this association of operators to observables, is supposed to be linear. When you apply it to the function 1, you should get the identity in the Hilbert space, and then you should have this very nice relation that relates the classical Poisson bracket of observables with the commutators in the space of operators, just like this. And of course, here we see H bar. So what we can do with these quantum observables is that we can observe their eigenvalues. And so these are the solutions here to this equations here. So we find states such that when you apply the operator, you just scale the state by a number. And furthermore, it also has a very nice prescription for what is the time evolution of the system. It is namely given by this very simple equations here. So the time derivative of the states should simply just follow the quantization of the classical Hamiltonian. So that is completely clear. Now, can you actually see the bottom of my screen, the last equation here? I can't see it myself. So that's, I'm sorry. I don't know what's in the way here. Maybe it's some kind of Zoom thing. So I can't really see the last line, unfortunately. Okay, so, but anyway, I want to press on. So I can't, there we go, yeah. So now, how is this really done in geometric quantization? Well, the first steps, as you all very well know, is extremely well written and presented in the literature and well understood. So we start with a general curved phase space. This is just another word for a general symplectic manifold. And then geometric pre-quantization proceeds as follows. There is, first of all, a quantization condition. And that says that if you take the cohomology class of the closed two form, the symplectic form is, you divide it by H bar, then that should lie in the image of the map from H2 with integer coefficients to H2 with real coefficients. Now, that thing is exactly the obstruction for the existence of a pre-quantum line bundle, which is a complex line bundle over M with a Hermitian structure and a Hermitian connection in such a way that this equation is satisfied. So the curvature of the connection is exactly minus I divided by H bar times omega. And so the Hilbert space in pre-quantization is simply just the L2 sections of LH over M. And we also have a prescription for the operator, so the construction that I just talked about before, hat. So F hat is simply given the following way. First of all, it's multiplication by F, but then it's followed, then there is added to this minus I times H bar of a first order operator where we stick in the Hamiltonian vector field of the observable F. And now these satisfies Dirac's third axiom perfectly. There is equality here, and so that's a very nice part about this scheme. However, there is a clear problem with this. So the two problems are really, and it seems to me, looking at the picture, that you can actually see the last line. So what's happening here is that, first of all, this does not reproduce canonical quantization, which the physicists are very happy about for Rn. And second of all, it also is a contradiction for Heisenberg's uncertainty principle. So clearly, this is not a sufficient theory. This is not good. However, geometric quantization also has a remedy for this. And so the general idea is to say, well, we need something like when we do canonical quantization, then we only consider functions of half the variables, say the momenta or the position coordinates. And so the general scheme for this is to choose a polarization. So a polarization is a Lagrangian subbundle of the complexified tangent bundle. And then we attempt to define the Hilbert space simply to be the smooth sections whose derivatives along the polarization vanishes. Now, if we do not have the P is integrable, so that means that if we don't have for all vector fields that are tangent to P, that the bracket is also tangent to P, so this is the violation of integrability if we don't have this, then we might actually end up in a situation where this Hilbert space is empty. So that's of course a problem. So we would want to require that the bundle is integrable. Actually, I should remark that there are ways around this, but I won't discuss this. So it is possible actually still to proceed even if we don't have this integrability, but that will be for another talk. But let me just illustrate this in a way that relates very well to canonical quantization, namely if we choose what's called a real polarization. So a real polarization satisfies that if you conjugate it, you get exactly back P again. And that means that there actually is a real subbundle of the tangent bundle, which is Lagrangian, such that when you complexify that, you get P. And so therefore, you will get induced the Lagrangian foliation on M if it's integrable. And so then this space of the Hilberts or the at least vector space associated in this situation are the sections of L which are covariant constant along the leaves. So for example, this works particularly well if I'm looking at a cotangent bundle and I'm looking at the vertical tangent space relative to the projection onto X. And in that case, the Hilbert space will simply just be, well, the pre-Hilbert space will just be smooth sections of X over X of LH restricted to the zero section of the cotangent bundle, which is just X. And then if you're given a volume form on X, you can of course do a Hilbert space completion of this along X. Okay. And so, by the way, this will, if this is done to X equals to Rn, this of course produces very well-known canonical quantization. So we're happy with that. Now, there's another possibility for polarization, the extreme opposite. There are many possibilities, but this is the extreme opposite. Namely, if you conjugate P and intersect it with P, then you get zero. And so those P's are in one-to-one correspondence with almost complex structures if I don't require integrability. And so those almost complex structures are compatible actually with omega, and that means that they, make the symplectic form a 1-1 form. And second of all, of course, it's squares to minus identity. That's part of being an almost complex structure. And now the integrability condition in this case here is exactly the same as actually saying that we have a Kähler structure and that the Kähler metric is related to the symplectic form in this usual way. And in this case here, I want to require that it actually is a positive definite Riemannian metric. Then it is Kähler. And so in this case here, it's very well known the proposal by geometric quantization is that you associate the quantum space, which is just holomorphic sections over Mi, so M equipped with this complex structure, and then you have an induced d-bar operator in the line bundle from the pre-quantum data and this I, and you just look at holomorphic sections. And if you have a volume form on M, so in particular, you could, for example, take the Liouville form associated to omega, then of course you can consider the completion Hilbert space, which would be take the holomorphic sections that have finite L2 norm and then complete that. Okay, now, what are the big problems in this? Well, the question which are not addressed by geometric quantization as it stands right now is, how does this depend on P? So the standard words that you will hear everybody saying in this field is, well, it really doesn't depend on P. P is just some auxiliary data, and you shouldn't worry too much about it. They are probably all projectively the same. I would like to say to the community here, well, our evidence for this is very limited, I'm sorry. It is limited to a few simple examples like flat space, quantization of moduli spaces, and I will give you actually a few more examples here where you have this. But I would contend that this is not the case in general. Okay, so what about the pre-Hilbert space structure? Which one should we actually use, and which one should we prefer, and so on? Well, no good answer from geometric quantization. You could, if you wanted to simply say, oh, I just choose this one here. But I will actually argue that this is not the right one always. Okay. And what about observables? How about quantization observables? Well, this almost always geometric quantization comes up with nothing, except for the simple cases. Okay. So for general curve spaces, there really isn't a general construction. However, what I will do in this talk here is I will give you answers to 1, 2, and 3, provided we have a Kähler structure on the symplectic manifolds we're considering. Now, not all symplectic manifolds admit Kähler structures. Thurston was the first to show us examples of those, say compact symplectic manifolds that don't have any Kähler structures. But I will assume that the symplectic manifold we have has Kähler structures, and then I will give you answers to these 3. I actually think that the theory also works for general symplectic manifolds that don't have Kähler structures, and you should work with almost complex structures instead. But again, that's I will leave for another talk. Now, the line bundle notation I would like to use is actually, I would like to switch notation. So I want to call 1 over h bar for k, and I will write L for L1, and then I will write LH as L to the K throughout the rest. Okay. And so we will write, the Hilbert space as H0 M L to the K. All right. Now, so the key thing that I want to try to consider is very general families of Kähler polarizations. And so I think this is an integral part of the whole discussion that I will present for you, is that I will not consider each Kähler structure one at a time, but I will actually promote the viewpoint that we need to consider families. So I'm going to look at a smooth map from some smooth manifold T into the vector space of smooth sections of endomorphisms of Tm in such a way that for every point in T, when I consider I sigma, so the point is called sigma, together with omega and m, then this is a Kähler manifold. Okay, so then of course I get for every sigma a subspace of the smooth sections of L to the K, namely the holomorphic ones. And so they will be indexed by T. So for the rest of the talk, I will simply assume that these subspaces for each sigma and T, for each family I consider, is a smooth subbundle of the trivial infinite rank bundle, which is just obtained by taking the smooth sections and crossing with T. And so the basic idea that I want to explore is that I want to seek to find connections in this bundle here, actually, sorry, in the sub-bundle. And the aim, of course, is that using these connections, I will use parallel transport along curves in T to identify the bundles. So this is a standard approach for trying to analyze the dependence on polarization. So let's see where this will take us. So let's make a few observations. First of all, if I somehow is given a priori from the beginning by somebody a Hermitian structure in this bundle here, well then, of course, I would, and I really think of this Hermitian structure as being very important in my problem and given. Then my connection will be, the parallel transport with respect to the connection will be unitary if and only if the connection is Hermitian with respect to the structure. So that means it solves this equations here for any two sections, psi1 and psi2 of this bundle of holomorphic sections. Very standard. And also further, this guy here, the parallel transport, is either independent or projectively independent of the choice of the homotopy class of the path from a sigma 0 to a sigma 1 in T, if and only if the connection is either flat or projectively flat. And I remind you that projectively flat simply means that its curvature is some two form on T tensor the identity acting on the fibers of the holomorphic sections. Okay. Now, very often we also have symmetry groups that we would like to quantize. So I might have classically a subgroup gamma of the orthomorphisms of the line bundle that preserves all the structure. So in particular, it induces some plectomorphisms of the base. And maybe I will also have that the group acting on T will be T again. So it parameterizes complex structures, this family T, and I want the family to be invariant under my group action. If that is happening, then projective flatness on the 2 here implies that we give a projective action of a pi1 of T extension of gamma acting. And of course, if we further have under 1 that the connection preserves the Hermitian structure, then this will produce a unitary representation. Okay. Now, let's see what we can do geometrically to try to construct these connections. So the first thing we can do when we have a family of Kähler polarizations, well, we can take a vector field on this parameter space, and then we can differentiate this family of complex structures. So we simply just take the derivative of it. And of course, the derivative at any point in T is again an element of this vector space. And a little checking will show that that endomorphism actually anti-commutes with the complex structure at that point. And so what that means is that that actually tells us that there is a unique element in this vector space here and a unique element in this vector space here in such a way that this guy here is the sum of those two, in fact, lying in direct sum pieces. So it's simply just saying that it takes holomorphic things to anti-holomorphic things and anti-holomorphic things to holomorphic things. There are no diagonal parts to the derivative. Okay, let me now assume that T is a complex manifold. So now I ask for a little bit more structure on my parameter space, namely that it is a complex manifold. Then I can make the following definition. A family of complex structures like this is holomorphic if and only if, when I take a vector field on T and I split it into its 1, 0 part and its 0, 1 part, and I use those to differentiate I get exactly the two corresponding parts in the decomposition here. This is what it means that a family is holomorphic. And in fact, you can remark that if you take the entire family of Kähler structures on a symplectic manifold, then that space admits a complex structure. And that family parameterizing itself is actually a complex holomorphic family in this sense. Okay. Now, let's look at our situation. So we have this sub-bundle, HK of holomorphic sections inside this trivial bundle here over T. So I always have the trivial connection in the trivial bundle. So what I am actually looking for is to perturb the trivial connection by some one form with values in the endomorphism bundle of this bundle to get a new connection. In fact, any connection in this trivial bundle will be of the form, the trivial connection plus such a one form. So I'm seeking, of course, such a U in such a way that it preserves the subbundle, because then parallel transport in that subbundle will give me the identifications I'm looking for. Now, I don't really want to consider arbitrary endomorphisms, but I really want to constrain this one form in such a way that when I apply it to a vector field and I look what kind of endomorphism it induces on this smooth sections, then it should really land in differential operators acting on these smooth sections. This is the very canonical assumption when you have infinite dimensional vector spaces of sections, that you are required that you are acting by differential operators. We'll see that that is really a very good assumption actually later on. Okay, so now what is precisely the condition for such an operator, such a connection, sorry, to preserve the subbundle? Well, there's a little elementary lemma one can prove, namely, such a connection preserves the subbundle of holomorphic sections if and only if U solves this equation here. So what it says is that for every section over T into the holomorphic subspaces, and for every vector field on T, and for every point on T, if you first take a sigma, you then take the d-bar operator of the connection in the pre-quantum line bundle, apply it to the section, and then you compose it with this endomorphism here on the form part, and to that you add the d-bar operator applied to your differential operator indexed by V here at sigma, applied to the section. You want that to be 0. That's exactly the condition. It's a little algebraic equation that you have to satisfy. Well, it's really not algebraic, of course, it's a differential equation. It's a partial differential equation if you wrote it out in coordinates. Now, there's a very nice little observation you can make. Namely, what if we constrain the vector field to be along the anti-holomorphic directions in T? Well, so then we know that this here, by the holomorphicity assumption we just made, is the same as this part of the derivative. Now, this part here, if we look right here, it has some part in T star of T, but then it has vector fields in T bar star. So when you take those vector fields and you contract them into the 1, 0 part, you will of course get 0. So actually we notice that this gives 0. So this part is 0. Well, then it is very easy to come up with a solution for this, right? You just take U of V double prime to be 0. Then this equation is satisfied. So therefore, what we see is that, you know, we can actually take U to be 0 in the anti-holomorphic directions on T. Now, this is simply just saying that if you take the trivial connection in the big bundle, in the trivial bundle, and you take its 0, 1 part, then that will induce a holomorphic structure in this bundle. So actually, these bundles, the holomorphic sections, actually automatically come with holomorphic structures. That's nice, because then, well, then we have that part solved. Therefore, we only remain with a problem in the 1, 0 direction. So let's assume now that what we really focus in on first is Hermitian structures. And one way to get Hermitian structures in these bundles is to fix a smooth function parameterized by T, but with values in smooth functions on M. And then you can consider the following kind of Hermitian structure in the bundle. The inner product of two holomorphic sections is the pointwise inner product. Then you multiply e to that function to the Liouville form, and you integrate over M. So this is not the standard inner product, but it is being twisted by this function here, which depends on sigma. So therefore, this depends on sigma. So that gives you a Hermitian structure in this bundle. And so then there is a very nice theorem that says that if you have a holomorphic bundle with a Hermitian structure in it, then there exists a unique Chern connection. So there exists a unique connection in this bundle in such a way that it's 0, 1 part is the given d bar operator coming from the holomorphic structure of this vector bundle we have, and such that the connection is compatible with this inner product here in the standard way. But the question immediately arises, of course, what is the curvature of this guy? And can we choose this guy, this emission structure in such a way that this maybe is projectively flat? And actually, can we write this guy as, trivial connection plus some differential operator? It would be very nice that we knew that this was given by differential operators. Okay, so the question, and these are questions, but the answers to these are very often not satisfied. I mean, very often this is not projectively flat. There is curvature, and it cannot be written just like this. Let me give you some examples. And so the example starts in really Grothendieck-Riemann rock theory. Let me assume that N and T are complex manifolds, and that pi is a proper holomorphic vibration over T. So this is the way that algebraic geometry would like to set it up. They would, of course, require that these are all algebraic, but we don't need it. We just need their complex manifolds. And let's say the total space is dimension M, and the base space is dimension R, so the fibers are M minus R dimensional complex manifolds. Let's assume that we have a holomorphic line bundle over N in such a way that if you look at all the higher cohomology groups of the line bundle restricted to all the fibers, you get 0. So everything is concentrated down in H0 in each fiber. That will imply, by elliptic regularity and so on, that there is actually a bundle of holomorphic sections induced over T, which is simply just the fiber-wise holomorphic sections. And if you now define T pi to be the kernel of D pi, so that's the vertical tangent space to T to N, then the Grothendieck-Riemann rock theorem tells you that the Chern character of this bundle of holomorphic sections can be obtained by first taking the Chern character of L to the K over the total space. You take the top class of the vertical tangent bundle, you cup those two together and you push it forward over this family. And so you see that, that this here will give you obstructions, because this tells you what the Chern character is. And so that's what I do here in the next slide. So what I do is, okay, so let's C be the first Chern class of L over the total space. Let us write the top class in its isotypical components which reflect to cohomological degree, so they're called TL. Then the Grothendieck-Riemann rock formula reads that the Chern character of this bundle here is a sum from D equals 0 up to R in cohomological degree on the base. And then you have L equals 0 to n plus 1 over L factorial coming from the exponential of the Chern character from the first Chern class, C to the L cupped together with this part of the top class and pushed forward. So for example, if you put D equals to 0 here, you will get the degree 0 part, which is the rank given by the usual Grothendieck-Riemann rock formula. But the higher degrees tells you what the first Chern class, the second Chern class, and so on are via the usual formula between Chern character and Chern classes. And so if HK supports a projectively flat connection, well then Chern-Weil theory will tell you that there must exist a C-twiddle on the base, a two cohomology class of degree 2, in such a way that the Chern character of the whole bundle is the rank of the bundle times X of that degree 2 class. And so if I write out what this means explicitly in terms of the C and these isotypical components of the top class, it simply says that the degree 0 part here, which we just discussed is the rank, right, times, then you take the degree 2 part in cohomology and you lift it to the D power, that must be via this exponential here, D factorial times the D's part of that expression. And so this provides obstructions for the existence of projectively flat connection in this case here. And now I want to show you an example that this really gives you obstructions. So let's take the universal curve over the moduli space of genus G curves. And so there, if you look at the cotangent bundle to the K, that's actually the pre-quantum line bundle over each of the Riemann surfaces in this case. If you look at the top form, the 2 form coming from this hyperbolic metric. And so if K is bigger than 2 here, you will have that the higher cohomology groups are 0 by ordinary Kodaira vanishing. And it has constant rank, therefore it generates a bundle. And a very simple computation will tell you that the Chern character of the push forward of this fiberwise cotangent bundle to the universal curve is given explicitly like this. And so these are coefficients, these are numbers, these are Bernoulli numbers. And right here you see the kappa classes. So these are the standard generators of the stable ring of the cohomology of the moduli space of curves. Now, these kappa classes are well known to be independent in degree less than G. They don't satisfy any algebraic relations. And so therefore, it is impossible for them to satisfy these algebraic relations. So you will not get a projectively flat connection in this push forward bundle here by this little example. Okay. Let me now somehow tell you what is the state of the art in terms of how far have we gotten with the constructions of these Hitchin connections, which I like to call them, because it really originates in Hitchin's original work here in 1. So what he did was he actually considered the case where M is the moduli space of flat equivalent connections on a surface, and T is Teichmuller space. And there he constructed a projectively flat connection. Now this family is what I have called rigid. I must say I somehow regret the notation rigid, because many people are asking me, so rigid means you can't deform, right? Well, you should think of it as the rigid family. So the family is very constrained, okay? And so maybe I should have called it a restricted family or something like that instead. But anyway, I will continue using the word rigid throughout the talk. I have generalized Hitchin's construction to general rigid families of Kähler structures, just basically doing a generalization of Hitchin's construction here. And together with 2 former students, in fact, 3 former students, sorry, we have generalized that construction, removed some assumptions on, in this case, to the metaplastic case. And that's actually highly relevant for quantizing parabolic modular spaces and its TQT applications, which I think that William talked a bit about yesterday. William is Mistegard right here. And then the 4th sort of generalization of this is we have managed to construct higher order operators, which really enlarges the possibility for which Kähler families we can apply this to with a former student of Rasmussen, but there are still constraints. And so what I want to try to focus on today, as fast as I possibly can get to it, is the infinite order differential operator constructions, which I will show you today, which really applies to general families of Kähler structures with no assumptions, except for the subbundle assumption that I'm making. Okay, so let's just start. So I want to remind you, what is this rigid? Well, if you look at the 1-0 part of the derivative of the complex structure, then you can always write that as some symmetric 2 tensor contracted with omega. And so rigidity means that this G here is always holomorphic. And that is extremely restrictive for a family. It basically means the family cannot be deformed much, and that's why I used rigid. Okay. Now, so the theorem says in that case, so if we assume rigidity, so G is always holomorphic. And if we assume 2 more things, which I call B and C, the first one is a kind of phenotype condition, namely that this cohomology class of omega the first Chern class of the manifold is proportional to the cohomology class of omega. And then the second one is that H01 of M is 0. If you have that, then you can actually prove that there exists a Hitchin connection in the subbundle of holomorphic sections. It's given by a 1 form on T with values in 2nd order differential operators. And if you moreover have that there are no holomorphic vector fields on M, then this connection will be projectively flat, and it will be projectively unique among 2nd order differential operators. That's okay. So basically a unique projectively flat connection. So it's as nice as you can possibly want. Okay, and in fact, it's even nicer because you can write down an explicit formula for the connection. Now, I don't really want to dwell with this formula. Just tell you that here there is really explicit formula. It's given by second order. Okay, so I talked a couple of times at this Geoquant conferences about this, so I don't want to dwell with this. I will skip this in order to get on. But another very nice theorem is that, or a property really, is that this connection is actually Hermitian with respect to a Hermitian inner product, which is exactly like I proposed before. So I know that there exists a smooth map from T over to smooth functions on M in such a way that when you write down this Hermitian structure, then that's preserved by the connection. And you can actually impose further things if you know that the first cohomology equivariant with respect to gamma acting on T and M of T with coefficients in smooth functions on M is 0, then this will actually be a gamma invariant emission structure. Okay. That deals with this case. Now we had assumptions A, B, and C. A was rigidity. We're not going to touch that for now. B, it was this phenotype condition. Now, that's possible to remove. And the new condition, what you have to do in order to remove this is to go to Metaplastic Correction. And if you do that, the new condition simply will just be reduced to that the first Chern class is even. So in other words, that the second Stiefel-Whitney class will vanish. If that is the case, then what you should do is consider a square root of the canonical bundle of your symplectic manifold, of your Kähler manifold, I'm sorry, for each point in the family. And there is a little issue here that there is some cohomological obstruction to constructing a consistent square root all over the family. It lies in this cohomology group here. But if you assume that that can be done, what you can do is you can now consider a new line bundle, which is L to the K tensor, this square root of the canonical bundle. You can consider holomorphic sections of that, and I will assume that that again forms a smooth subbundle of this bundle here. Now you notice that this space here depends on sigma, so it's no longer a trivial ambient bundle I have, but it actually turns out that there is a construction of a reference connection in that bundle. And so I can do the similar thing as I did before. I can namely take this reference connection and look for one forms on T with values acting in differential operators acting on this tensor product here. And I can ask myself, can I find a U such that it preserves this subbundle holomorphic sections? The answer is that if A and C are satisfied and the second Stiefel-Whitney class vanishes, then there exists such a U that preserves HK. There is not as explicit a formula for it. We know what the leading order term of it is, and then it has no first order term, but it has a zero order term, which is implicitly given in this case. Okay, and actually we can say something about projective flatness. And in the interest, let me see, in interest of time, I'm going to skip this. Okay, this is a recent theorem together with William Mistegard. And there is certain conditions. I will namely get back to these maps on the level of smooth sections in a second. So I'm going to skip this. But there is very nice results about when this is projectively flat or not. Okay. But so far, I have not touched this rigidity assumption. And that's really, really limiting this. Let's have a look at it. So, you know, we're assuming that G is a holomorphic section of the second symmetric power of T. Now, it could be, for example, if you're looking at a Riemann surface, then you will get that this is 0. And what happens if this is 0? Well, that means that G is 0. That means that the derivative of the complex structure in the 1-0 direction is 0. So that means you can't deform the complex structure at all. So this is extremely limiting. So as I wrote down here, if you have a Riemann surface of genus bigger than 1, then there will be no sections of the second power of the tangent bundle. So this is very limiting. So we really need to remove this rigidity condition. And so now let me start embarking on how we should go about removing this. So I have again a general family of Kähler structures. And so what I'm going to consider is the following linear map. So it is something that maps symmetric tensors of degree L to degree L minus 1, but then it tensors on this the anti-holomorphic cotangent bundle. And it's extremely natural map. It is namely I times K, remember K is the power of L. Then you take the degree of the symmetric tensor L and times omega, the symplectic form, plus L minus 1 times the Ricci form for your Kähler manifold, and you contract that into the symmetric tensor. So it is indeed a map that goes from here to here. And now what you get, so I will get back to why I defined this map really shortly. But what I'm going to do also is I'm going to look at higher, so my aim is simply to look at higher order operators. And so the higher order operators I will look at is an operator of degree L, and it takes in such a symmetric tensor of degree L, and it maps smooth sections of L to the K to itself. And the formula is given explicitly here. So it's an iterative definition. So if you've already defined it for something of degree L minus 1, then, sorry, it should have said L minus 1 also here. So what you can do is you can take, if this tensor is locally written as x1 up to xl, then you can stick in the last L minus 1 into what you've already defined and compose it with our connection in the bundle applied to the first guy minus, and then you take this first guy and you differentiate that with respect to the Levi-Civita connection in this tensor bundle on the manifold. That gives you a new tensor of degree L minus 1. You stick that into nabla L minus 1 here. So that's an iterative definition of order L operators acting on this given such symbols, such symmetric tensors. Okay, and now here's the main point. So you also consider the divergence operator. So the divergence operator really works on tensors, and so it's given iteratively like this. So if L is 1 and 2, you simply just take the Levi-Civita connection, you differentiate the tensor, and then you trace the one form part into the first entry in the tangent direction. And for L bigger than or equal to 3, you have the following recursive definition. Okay, and now the main theorem, the main calculation behind this says the following, and this is joined with my former student Rasmussen. If you take a degree L symmetric tensor and you take a holomorphic section of L to the K, so we're fixing some sigma in our family, so we have a Kähler manifold. And if you then do the following, you take GL and you apply this Lth order operator, but you modify it by an operator of order L minus 1, which is exactly this divergence of this guy, and then stuck into this L minus 1 degree operator. You apply it to the holomorphic section, so you get a new smooth section of L to the K, and you apply the D bar operator to it. You don't get 0, but you get the following. You get nabla L applied to the D bar operator applied to this, plus this psi L applied to GL. So this is a very important formula because this allows us to do the following. So let's focus here first. Let's take let's take a smooth function on M. And so I will start a recursive system of tensors by starting with F itself. That's a 0 order tensor. And then I will take the D bar operator, apply it to that. So if F is not holomorphic, I will get something there. And then I will assume that there is a tensor such that when I apply CL to it, I get D bar of that. And then I continue doing this over and over and get a higher order tensors. I will assume this set of equations can be solved iteratively. Let's just have a look at how reasonable that is. If I go back to here, you see that what I'm contracting with is K times L times omega plus L minus 1 times the Ricci form. So if K is big enough, this form here is invertible. So it's not a problem to solve these equations here if K is large enough. And it could well be possible always. But we can certainly see that uniform in L, it is possible with large enough K to solve these. Okay, so you solve the system here. And then you define f hat to be this operator here. So this is an infinite sum of higher and higher order operators. So I am proposing this as the operator in geometric quantization, which replaces our usual pre-quantum operators. And the reason is the following, that if this sum makes sense and converges, then it turns out that it actually maps holomorphic sections to holomorphic sections. It is constructed in such a way. I'll give you the argument on the next slide. But at any rate, what I can always do is I can always look at the Fs for which this is possible. So let me just show you the little argument. So if I just formally, for the moment, not worry about convergence, just look at the d-bar operator applied to that, and I formally move the d-bar operator inside the sum, and I apply my formula, then the recursive equations are exactly made in such a way that this tensor here is 0, so I get 0, so it preserves holomorphicity. And so that allows me to define a subspace of the observables, namely, I call it OK sigma. This is the space of quantizable observables. These are the spaces exactly for which these tensors here can always be found, and the resulting operator really gives you a well-defined linear map here. And so this would be vacuous if I couldn't establish that this really works in some cases. And so let me show you the following theorem. If you assume that M has an analytic structure because it has a Kähler structure, and so if you take the underlying real analytic structure for that, then it turns out that all the real analytic smooth functions actually are inside this ring of observables. So you can quantize all real analytic functions. So what may fail is that some smooth functions may not be quantizable, but all the real analytic ones are. And moreover, we satisfy this usual deformed version of the Dirac conditions. Well, this is not one of the Dirac conditions, but the very usual one, right? That if you compose the hats of 2's, you get the hat of the multiplication of the functions plus a correction 1 over k. And this one here is the deformed Dirac condition. Now, let me just very quickly make a few remarks about how this works. So if you just look at this series here, and you assume that you have a real analytic function f, then it turns out this series is divergent. But it turns out, however, that it is only factorially divergent. So that means that this thing here, if you take and divide by 1 over L factorial, then it diverges. Now, if you just divide by 1 over L factorial and look back at this equation here, you destroy this equation. It won't work because you see there is something going on about, some telescoping thing here where you combine the various orders. So that wouldn't work. But it is true that if you divide by L factorial, this becomes summable. And so the answer to how you should deal with this is exactly resurgence and Borel Laplace resummation. So let me just really quickly remind you about how we deal with some divergent series in mathematical physics. They are very common. They show up always with path integrals almost. And so what you typically are given is you're given a divergent power series, and you really would like to somehow construct a holomorphic function in some disk D in the complex plane in such a way that when you do the asymptotic expansion near 0 of that guy, you get exactly your series back. And Borel Laplace resummation is the solution to this problem if the series you start with is factorially divergent. So let me just show you what is the Borel transform. Well, the Borel transform acts on these formal series the following way. So if Borel applied to z to the minus alpha minus 1 is simply zeta to the alpha divided by gamma of alpha plus 1, so also written like this. So here gamma is the usual gamma function. And so this shows you how to define it for non-integer also values of alpha. And what is the point about this? The point is that if you consider the Laplace transform, so if you look at some contour gamma in the complex plane, and you have a holomorphic function, then we might attempt to define L gamma of G to be the contour integral along gamma of x bar minus z zeta, G of zeta, d zeta. There's a bit of d here. And so if this is a convergent integral, we can define this function this way. And it turns out that this is certainly possible in pure powers because of this fast decay you have here. If you, for example, looking at the real positive line, and you get these very nice thing here, namely that this Laplace transform is a formal inverse to the Borel transform, which was a formal transform on series. So therefore, there's a little proposition that says if you start with a series here, and you assume that this Borel transform here extends to an analytic function around, appropriate neighborhood of some contour like this, then you can define phi hat to be the composition of the Laplace transform in this along that contour, composed with the Borel transform, so just like this. And very nicely, this function here will be analytic in some half plane specified like this. And moreover, its Poincare asymptotics, when you expand at set going to infinity, will be exactly your series here. So in this case, I'm expanding around infinity instead of 0. And moreover, this composition here behaves very nicely with respect to derivatives. Okay, so this is a very common thing. And so there's actually been done lots of work on this. And one of the main players in this game is Kähler. And so what typically happens is that this function here is multi-valued, and it satisfies very interesting jumping phenomenon when you go across the critical points in the plane. And Kähler, in fact, has developed his theory of resurgence, which is exactly a machinery to compute these jumps, and they're computed in terms of what he called alien calculus. And so it's a very beautiful, very complicated package that he has provided to deal with all the peculiarities of this. And in many ways, the peculiarities, namely these jumps, are very, very interesting, because many times these jump phenomenons, if you just know the jump phenomenons, that allows you to actually define what the sky is. Okay, but leaving this aside for now, I don't want to dwell too much with this. I just want to sort of remind you a little bit more about Kähler's theories. So one of the aims was actually to understand solutions to differential equations. And so this is very similar to my application. That's why I just want to mention it. So very often you might have a formal power series solution, just like in WKB approximation to the solution to the Schrödinger equation, which is just a formal solution. But then what you can do is you can actually apply this Laplace-Borel resummation under favorable conditions, for example, factorial divergency, and you will actually get an actual analytic solution to the equation. So example, if we take Euler's series like this, clearly factorially divergent series, it's a formal solution to the following ODE. But it's very nice that if you look at the Borel transform, then it's a very nice function. In this case, you see it has a singularity as -1. It is actually single valued in this case here, so it's a little bit special, but still it has the singularity. And it's certainly analytic as a function of z goes to this here when the real part of z is positive. And it actually solves. It's an analytic solution to the equation. So now let's apply this theory here. So what I want to do is I want to define the Borel transform to be this series here. And I said to you before that if I divide by L factorial, this is actually a nice convergent series. And provided that F is real analytic. And so if F is real analytic, I get an analytic function of zeta in some wedge around R plus actually. And so what I'm going to do is I'm going to apply the Laplace transform to this, and I will define F hat S, because now everything depends on an auxiliary parameter S. And so one can actually show by a little bit more computations that this guy here actually takes holomorphic sections to holomorphic sections for S in this wedge. And so therefore we actually have a construction of operators for real analytic functions via Laplace-Borel resummation of this series here. Okay. So for the rest of the talk, I will suppress these sub-indices here. Okay. So I will just proceed as if we are constantly doing this Borel Laplace resummation. Okay. But I will just be working with the series without this Borel resummation applied to them, because else we won't manage to finish the talk in time. So let's get back to it. So this was a construction of observables, quantization observable. What about if we have a family, and what about identifying things in a family? Well, let's try to do that. Let's try to see if we can construct these connections. So we are going to start by having some one form. It could be, for example, 0 if you want to. But I'm going to start with some one form with values in smooth functions. I'm going to then iteratively define GKLAs by solving the following equations. And notice they are almost the same as the equations I had before for functions, except there's this little term here added here. And this little term here is added in such that the way that it doesn't solve the Debye equation, but it solves exactly the equation for preserving holomorphicity, as I wanted for a connection. And so, and the whole thing starts with this, initial given one form. And so then what happens is that you can consider this now one form on T with values in infinite order differential operators given like this. And so the whole story proceeds the same way. I can use Laplace-Borel resummation, provided I have certain real analyticity of the function, the one form here I start with. And if that's the case, then I will actually solve this equation here. So I will actually get induced Hitchin connections this way. So this allows me to make a definition. I can look at the subspace of one forms for which I can solve all of the iterative equations and such that the resulting operator is well defined on holomorphic sections. And so that AT then parameterizes Hitchin connections. And notice I just remarked that if this guy goes into real analytic functions, then it can be solved. Okay, so this gives me a large space that parameterizes Hitchin connections in these bundles. And this is for general families now. So we get lots of Hitchin connections. Okay, so now what happens if we start with a form that is K-dependent? We can certainly also do that. And in that case, what will happen is that if we have the following, that if you differentiate this one form on T and that it is 0 up to a correction term, which is 1 over K, then you will get an asymptotically flat connection in these bundles. And correspondingly, if you just have that the derivative is a one form, so it has nothing in the endomorphism part, then it'd be asymptotically projectively flat. So remember, because we're doing things very generally now, we cannot expect to get flat or projectively flat connections. But what we see actually is that asymptotically, as case goes to infinity, we get projectively flatness. Okay. Now, so what's actually going on if I just take the usual case that I considered in the beginning? So actually, all the way through so far, what has happened is that people have, just like Nigel, started with something in degree 2 and then tried to come up with correction terms of degree 1 and degree 0 in such a way you preserve holomorphicity. But somehow the main idea that I have here is actually start different. Start with whatever function you want and then solve the system backwards, upwards. And actually, if you do the following, if you take the one form, A, which is simply just the derivative, or this is the Ricci potential, then what happens is that you will actually build the system that is exactly Nigel's solution, and it terminates at second order because he's assuming that his G is holomorphic. But in general, it will not terminate. It will just keep going, and you will get infinite order operators unless you have something very special as rigidity of the family. Okay. Now, the same thing goes with Hermitian structure. So I will finish in 2 minutes. Okay, so I started a little bit late because of the little introduction. So please allow me 2 minutes. So if we have functions on M parameterized smoothly by T, we can make these Hermitian structures like this. And I'm now going to assume that you also have an asymptotic expansion in 1 over K of these guys. So if you have that, then there is actually a way to, well, of course, then you can always look at the Chern connection as I explained earlier, or compatible with this inner product here. But then the theorem says that if you have such an expansion of H here in terms of powers of K inverse, then there will exist a corresponding expansion of differential operators of infinite order in such a way that if you have AK, the one form on T with values in functions defined this way here, then that will induce a Hitchin connection. And this Hitchin connection is the Chern connection. So I can actually understand in terms of infinite order differential operators, what is the Chern connection in this situation here? Okay, so this gives me now somehow a proposal for a scheme for Kähler quantization in geometric quantization. You start with the usual setup. You do the usual pre-quantization. But then when you want to quantize, what you should do is you should not choose one complex structure or two. You should choose a family of complex structures. What you then choose, and there are several possibilities here, but one way is to say, I'm going to fix what is going to be my Hermitian structure in the bundle. So I'm going to fix this function here with an asymptotic expansion like this. That will tell you that there is a Hitchin connection in the bundle, which is the Hermitian connection. And more importantly, it will also tell you that there is a gamma equivalent linear map from A into functions like this in such a way that if you apply this dA first and then do the geometric construction that I showed you before, which is the construction of observables, then those are preserved by the Hitchin connection. So they are, the quantization observable is parallel with respect to the system of Hitchin connections. And so what I want to emphasize here is that the whole quantization scheme really depends on the choice of T. And the bigger symmetry group you have, this will force you to get a bigger T. But the thing is that the bigger the space of observables you want, the smaller T you should choose. So for example, if you choose T to be just one single Kähler structure, then you can quantize all real analytic functions, certainly, and possibly some more. But if you, for example, choose T to be the entire family of Kähler structures, I actually conjecture the only functions you can quantize is the constant functions. So there's kind of a trade-off between how big a T do you want. But the nice thing is that everything is compatible within this family. The quantization at each point of the functions is compatible with the way you identify the Hilbert spaces over this family. But there is no guarantee that the connections are going to be projectively flat. In fact, I think it's very important that the holonomy as you move around in T will give you endomorphisms acting on these Hilbert spaces. And these are important for the quantization. So in other words, if you take the metric of space and you move it around some closed loop in space, you will get a holonomy, and that holonomy will be important and will be sensed in the quantum system. And finally, the same thing goes with symmetry groups. If you want something huge symmetry, like all the symplectomorphisms of the manifold, well, then that will force T to be the entire family of Kähler structures. And so you get a huge symmetry group, but it'll hurt you on the functions. And so that's what I'm saying here. Then A will only consist of the constant functions on M, if M is compact. So that's my new proposal for geometric quantization that really works with observables, quantizing observables. There's also a way to quantize Lagrangian submanifolds in a similar way. So it's a very nice package where you have families, you have compatibility for varying sigma over the family, with quantization of observables and with quantization of symmetries and Lagrangian subvarieties quantizing into states that are parallel with respect to the connections. So thank you very much for your attention.
Are there questions?
Yeah.
Hi. You hear me? Yeah. So I have the question.
Hi,
So of course, if you have families of complex structures, you know, of course, that one also can, of course, do the triplets operators.
Yeah.
Complex structure. Now my question is, how is this related to your new suggestion? I guess there is some relation there, but how do you know it already?
No, I don't know it. I have also speculated about how these two things are related. I don't know. But what I can say is that typically, as you know, right, if you consider the Hitchin connection, for example, in the rigid case, then the turbulence operators are not parallel with respect to the Hitchin connection. They are asymptotically parallel, but not parallel. And so here I'm actually providing something that is parallel with respect to the Hitchin connection. So my proposal for the operators here cannot be in such a way that they are exactly the Toeplitz operators. But what I might expect is that these operators maybe have an asymptotic expansion in terms of Toeplitz operators, where it starts with the Toeplitz operator of the function, and then there is a correction term in 1 over k times some other function. And I am, in some cases, I can prove that that next term is the Laplace operator applied to the function. Okay, and then expect the whole asymptotic expansion 1 over k.
So that is interesting. I also would expect something like this, I have to say so. And when you say that's very interesting, because this is the relation. So with between Toeplitz operation quantization and geometric, also this Laplace operator is also the second term of the operator of geometric quantization. So it's very, very interesting relation, I guess. I think one should really have people look on this proposal there. So I bet there's a deep thing involved. Okay.
Yeah. Good, and I think it is also very interesting to understand how does this relate to deformation quantization. So there is, really, I mean, I expect this to relate just as nicely as you have proven with Karabekov of the relation between, Toeplitz quantization and then deformation quantization. I really expect that there is a very similar story here, although I have not worked it out yet.
So are there more questions? I've seen that there are two online participants raising their hands. So go ahead, unmute yourself, and then we will.
Yes. I have a question.
Sure.
So first, thanks, Jørgen, for this nice talk. So my question is really about the Borel Laplace transformation approach to these quantization of operators. Sorry, quantization of observables.
Yeah.
So first, do we have any thoughts on what is the meaning of this, of the Borel plane of this variable S in this context? What would be the singularities? And second, if we consider again the setup of Jørgen-Simon's theory, then if you apply this quantization approach to Wilson loop operators, you should get operators on the associated Hilbert spaces. Should this give a new approach to quantizing Jørgen-Simon's theory, and how would this compare to Witten-Reshetikhin to Reiben variants, do you think?
Yeah, so several questions, right? The first one is, what is S? And so I believe that there is a relation between this quantization and then the brain quantization that you're very familiar with Gukov. So you see that what's happening here is that I'm utilizing another way of talking about these tensors is actually to talk about the cotangent bundle of the manifold. And so if the cotangent bundle has a hyperkähler structure, then I believe this parameter S here is a parameter on this hyperkähler sphere. Much like what we're seeing in the the complex Velinde formula, that there it's called T. But I believe that that's this extra parameter that we are getting when we quantize hyperkähler manifolds. And so this is what I really think that's going on, is that this is a parameter just like Witten and Gukov have when they do their brain quantization. And in many ways, I think this is maybe what they mean in terms of explicit formulae when they talk about brain quantization. Because notice that this provides the structures that they are asking for in this more sort of, I would say, axiomatic discussions that they are having about brain quantizations. Because in concrete cases, I don't really know how to exactly do those things because they are sort of abstract. But this provides very concrete answers for what one should do. And I believe it's very closely related to brain quantization. And so I think that it is indeed opening up the relation between the usual Witten-Reshetikhin to TQT for SU2 and then the quantization of the Higgs bundle moduli space via this hyperkähler structure and the discussion in that direction. So yeah, that's what I think.
Okay, thank you.
There was another online question.
Yes, thanks a lot for this interesting talk. My question concerns like one of the assumptions that you made at the very beginning, where you assumed that this family of Hilbert spaces is a smooth subbundle of the trivial bundle.
Yeah.
And kind of like, is this not already assuming some form of independence of the quantization of the, like if you need like locally trivial, then it means that if you vary your the sigma and the t like a slightly bit, and you still get the same quantized Hilbert space, right? Like that's.
So let me just see if I can find it where I wrote it. There. Well, but how, right? So the tangent bundle to a manifold is locally trivial. But that doesn't tell you that there's a canonical identification of the different fibers of the tangent bundle, right? In fact, the curvature of the metric is an obstruction to producing a flat connection on a Riemannian manifold that is compatible with the metric. And so here we really want to know precisely which unitaries relate to Hilbert spaces. It's not enough to just, for example, if all the fibers, if we're talking about compact manifolds, then what you just said could be just rephrased as saying, oh, well, the dimension of this space is independent of the complex structure. So therefore it's independent. Well, I mean, what linear maps between the vector spaces are there exactly?
Okay.
Because there are many choices, right? And so, and you see you're quantizing observables. And so you really want to sort of have a very nice correspondence that says that I quantize observables for this complex structure, I quantize for this, but I want to know that also the parallel transport, takes the quantization of observables here to the quantization of observables here. And that is not at all clear that that can be done. And in fact, I showed you obstructions to it via this Riemann-Roch computations.
Okay, thanks. Yeah, that makes it clear.
But you're right that it is some assumption, right? I mean, it's a very technical assumption. That's what I'm saying. It's really just a very technical assumption. In fact, if we have compact Kähler manifolds and all the higher cohomology groups are 0, this is automatic, this assumption.
So you also don't have any example where this assumption is violated?
I think there are non-compact, well, I mean, there is certainly ways to violate this. Namely, if you take a family of Kähler polarizations where H0 will jump up. And that's possible because what could happen is that at some special fibers, you could have H1 and so on. And there might be a way to remedy this by considering, more advanced considerations where you consider superspaces and you consider the higher cohomology groups also. And you understand that there's really a superspace. But I wanted to avoid these discussions. Okay, so we should settle this case here first, really, with the quantization before we go to the supersetting. But of course, this would be next steps is to consider the supersettings, because then at least when we have compact symplectic manifolds, we know by elliptic theory and Fredholm theory that the supersetting always provides bundles.
Okay, thanks.
Okay, there is a question from Freiburg, yeah? Yeah.
Hello, I don't know if you can see me.
I see a very small waving hand at the second row on the picture.
I'm not very tall, it is true. But so my name is Pierre Bieliowski. Okay,
hi.
For this great talk, very inspiring. So my question is probably related to the question Martin asked you. I base my question on the example, which is a little bit out of your framework of geometric quantization, on the example of the quantum torus. And so you know that when you have this family of C-star algebras on this parameter space, right? You know that the family of these algebras, of course, the two algebras are not isomorphic in general, and even not Morita equivalent.
Yes.
And you have this action of the arithmetic group on the parameter space, which gives you actually the family, the parametrization of the Morita equivalent classes of your C-star algebras. And I was wondering your framework, but I understand that it's a little bit different. context than just this C star, infinite dimensional C star algebras. For example, in your case where n is compact, you will have only, if you look at this tuplets quantization, you will have only a finite dimensional C star algebras. But let's say in a non-compact case, and if your T and your map I are adapted, and some examples, let's say, do you have some examples where you can actually say something about the Morita equivalence classes of the different quantizations in terms of C star algebras, if you have some, so some action of some symmetry group, let's say, on your T, on your space, which parameterizes this kind of things.
Yes. So I should just say that I do not have explicit examples to tell you about here, but indeed I can confirm that this construction here is very local, right? So it does not require that M is compact. So we could very quickly get into situations where, you know, the full theory of C star algebras is really super relevant. And basically, so in the case of C star algebras, we are not considering so much representations, right? We are just considering the algebras. And this would correspond to really focusing in on, you know, taking two observables, making the construction of the operators, as I'm doing here, take the product of the operators, and then understand that you can invert the construction in such a way that you can take the inverse of this construction and get now a new element so that you get a product, a, say, deformation quantization, or if you're more lucky, really a product in a C star algebra. And so I think this is doable. I have not worked so much in this direction. There will be nice examples where there will be very nice, well-known products coming out, but also very new ones, I imagine. So I think this is the way it links to the context that you are discussing here. But I do not have concrete examples yet of this.
Okay, thank you. Oh, I have another question. So I Googled you, and I couldn't find a clear reference to what you told us today. Is there
It's not published yet. So I'm writing this paper at the moment.
Okay, thank you.
But I mean, what I can say, if we just go back here, so a lot of this is published. So, you know, 1, 2, 3 is published. Some of 4 has appeared, some of it in Rasmus's thesis, but the rest of 4 and 5 is not published yet.
Okay.
It will appear in the archive soon, I hope.
Okay, thank you. Thank you.
You have a question? Okay. So, hello, Jørgen.
Hi, Martin.
For your very inspiring talk. I have a lot of questions, but you have no time. And first, and there is a remark. I mean, your QLs there, they smell a little bit like deformation quantization. You have different operators, and it just a remark. We saw in a completely different context that these iterated covariant derivatives, if you symmetrize them, they can be seen as an asymptotic expansion of composing in some sense with the exponential map of the Riemannian manifold. So this may perhaps say go into a direction of a say less divergent, but this was only my second question is you may perhaps help me with a psychological problem. So of course I started with physics and then I was strongly against physics. And for instance, in the text, in the old American textbooks, somehow in an explanation of in quantum mechanics, you find the word multi-valued functions, but it's just an excuse because they wanted. And so for me, it was physics speak. And then recently, and this was due to a remark by Sebastian Goethe, I found in a very early work of Pierre Deligne that actually in complex analysis, this is really taken serious. So they're talking about multi-valued things, and Deligne even somehow defined it in some way. And just could you comment on this? I mean, multivalues thinks that you have a function which is not, has many values, and can you view this, and this is the question, as say a section on some coverage space or a function on the covering space?
Right. So to answer the last part first, indeed. So this multivaluedness is everywhere in Kähler's theory, and they're talking about resurgent functions, and they have a very general definition of what that is. But in what I am doing here, the following definition suffices, namely that it is so it depends on this parameter S, and S is running in the complex plane. But in fact, S is not allowed to stay to hit certain set of singularities, and this set of singularities can be very complicated. But typically, it could be discrete. It's not typically discrete, but it could be discrete. And you can simply think of the function as being defined on a Riemann surface, which is a branched cover, maybe infinitely order branched cover, over this plane with branch points at all of these singularities. And so that's simply the way you should think about these expressions in S. So let's see here. So here, this S here will be running over a possibly infinite cover of the complex plane branched over an infinite number of points in the plane.
And this is
it's single valued up on this cover.
So what you are saying is that this branch cover, it's the data is given if you do the Laplace Borel summation, then these geometric data are given, and so you can legalize it. Okay.
Yes. So what happens is that you make this Borel transform and you start studying this expression. And so what you will find is that it is convergent. So you know, you start analyzing this analytic function, and what you will find is that it has certain singularities. And furthermore, when you start parallel transporting it around curves in the plane around these singularities, you will find that it changes by a certain amount. And this certain amount actually can be obtained by what's called alien calculus. So this is the jumping phenomenon I was talking about before. And in many cases, one can set up a whole system in such a way that actually you are looking at a Higgs bundle on this plane, which it has on the cover of the plane, whose monodromy is exactly given by the jumping phenomenon that Kähler is talking about. So in some way, this becomes a Higgs field.
Okay. Thanks. So this may help me to get over this. The last question is just so I drop some words. So you have you parameterize your polarizations by some family, and there's also back there to the 80s or 70s, there was this Blattner constant Sternberg things where people there was an attempt for real polarizations to get more observables, more good observables than just linear in the momenta and constant in the momenta, by also talking about families of polarizations. Is there any relation with this? I mean, of course, here you have the Kähler situation, but
right. Mm-hmm. So I mean, for example, if we take flat space and we still stay with the Kähler situation, then indeed there is, because what happens is that you can then quantize a little bit more than the ones that just preserve the polarizations. You can actually quantize the second order ones also, because they preserve their Hamiltonian flows, preserve the family in that case. And so then what you can do is you can really quantize observables in that case to second order by moving the polarization and then using the Blattner-Kostan-Zerilov formula to come back to the polarization you started with. And so the point is that this pairing is nothing but parallel transport from one fiber to the other in a product.
No.
And so this is the way it's related to the connections and the parallel transport.
Mm.
Yeah, this is just another way of trying to formulate this problem here, but I find it very difficult to work with because I don't know what the pairing should be in general and so on. But I imagine that in the long run, we could possibly turn this into pairings, just the way I said, parallel transport and inner product, and then you will get the pairing. But the thing is that the pairings will be given much more globally and more difficult, whereas these operators here are given by local differential operators. So it's something one can easily manage, I would say. And second of all, it does not, well, I mean, yeah, it's for me, it's just much simpler to work with these connections.
Okay.
Because parallel transport is obtained as solutions to PDEs, and so much more difficult to work with than the actual PDEs. So when you work with connections, you just work with the PDEs and not their solutions. You implicitly work with their solutions. But also coming back to your first question, I think it would be very interesting to try to understand, you know, and also to Pierre's question, namely, I take such two operators, one for G hat and one for F hat. I multiply the two together. This is very easy to do, you know, formally. And now I rewrite the result in terms of of this hat applied to some function, and I define the star product this way. And I think one should, you know, obtain explicit formulae in terms of the Levi-Civita connection on the manifold in terms of which star product you are obtaining here. Because this is local.
Yeah.
And makes sense on non-compact manifolds.
Okay, I think we are already half an hour over time, so I suggest.
Sorry.
I suggest we thank Jørgen again.
Thank you.
So, and